So welcome back, everyone. So let's get started. So we're going to be talking about linear regression today. This will, so other than finding the mean of a data set, this will be the the first class of techniques within data analysis we'll talk about. So just to look at this, so the schedule a little bit. So the stuff we'll start with today will just be mostly the problem formulation, and so we'll also look at a very simple solution of the problem. So today we'll just be thinking about this data like in 1 or 2 dimensions, which is the simplest version. There's a little bit more so pictures you can draw, you can understand the structure of what's going on, and then after today we'll get into the into the higher dimensional version, and also the polynomial regression. So as you'll see, kind of once you understand the basic foundation in today's lecture, and then you apply like the power of linear algebra on top of this, the generalization to like higher dimensions and to polynomial regression is going to be actually quite straightforward. Then we're also going to see one of the most powerful techniques within data analysis, which is kind of what so I think generally really differentiates things like machine learning from more classical statistics is cross-validation. So cross-validation is what we'll talk about on Tuesday next week, and this is the way of trying to evaluate how well is your data analysis working. And this is, it's not a completely new idea. It's from like the 1960s, but it really picked up steam in like the 1980s, and now it's like the default way of kind of evaluating what you're doing in data analysis. And so this is this thing from like in the world of like statistics with frequency statistics with like hypothesis testing and so forth. This is a different idea that goes back like 100 years. This is a much newer idea here. And so then we'll have like a little review in Slack before fall break. What we'll talk about in regression, we're now into the techniques and not as much review for people who've had linear algebra or probability in the past. So the intention is to go a bit slower and more gradually. I'm sure some of you have probably seen linear regression in some way before. I'm hoping, I believe you'll get a new perspective on some of these things as well in this course, and definitely a very foundational view of how it's working and what it's trying to accomplish. The stuff I'm teaching in this course is stuff that when I was learning about this in school, I was not necessarily taught all these things. I had to kind of discover them on my own. So I think this will lay a important foundation for not just using regression in general, but also for kind of the techniques we'll see here are going to be kind of simpler versions of things that will show up in the rest of the class as we move on to more advanced topics. Okay, other things that happened. So quiz 2 came back. The quiz 2, I think, was more in line with what we were looking at. The average score was higher. The average, I think, time it took someone on the quiz was closer to about 17 minutes. Which is more what I have in mind. So I think So hopefully you also maybe spend a bit more time reviewing and preparing for it. And so that's the intention of the quizzes, to force you to kind of having to review the material and make sure you're up to speed at various points in the class so you don't fall too far behind. So great. So homework 2 is also due today. So at the end of the day. So it seems like there have been a number of good questions on Canvas. I think people are, in general, seems to kind of, this is maybe more straightforward than the first homework, perhaps. So again, this homework is meant to be kind of, so traditionally how students have viewed it, this material and this homework is a bit simpler than, so what will happen in homework 3 and 4. We'll post homework 3 in about a week or so. And you'll have basically 2 weeks or a week and a half after fall break to do it, but we'll give it to you earlier so you get a chance to start working on that before fall break if you want to. This one will have kind of, is going to be a bit more complicated, so synthesis of ideas that have been building over the course. And so that makes it, you need to kind of understand a lot of stuff building up to that point to put it all together on this homework. And that'll be especially true in homework 4 as well. So kind of, if these first 2 homeworks happen to be super simple for you, these next ones might be slightly more challenging. So keep that in mind in planning the amount of time you allocate to complete them. So there's non-explicit midterm. There are the quizzes. There are the 6 or 7 if you count quiz 0 throughout the semester, and then there's a final exam in the end. Right, so there's not a midterm right before fall break, but you will have a quiz 3 right before fall break. That'll be in, I suggest again you take it in class, like like I do all of the quizzes. So great. I think that's a bit for the schedule. Oh, so another piece of good news. It's been 2 weeks since my bivariate booster. So I'm not wearing a mask before and after class. Before I made a personal decision. I think my risk of this is now, of getting very sick with COVID is now sufficiently low that I'm, not wearing a mask before and after class before. I respect all of your own, decisions on how to handle this, but, so in case you're wondering about that. Okay. So let's get on with the lecture. So linear regression. This is about. So we're going to start with. So the input to this problem, all right, is going to be some data, and I'm going to write this as uppercase X and lowercase y. In this lecture, X is going to be a vector and Y will also be a vector. And that's why I'm writing them as lowercase y, but I'm just going to, I'll also think of X as like a set. And in the next lectures, X is going to be, each is going to be a set of vectors themselves, or is actually going to be a matrix. So I'm going to keep it just as an uppercase, just so the notation is consistent here. And so we're going to think of X, and for now, we're not going to think of it as a matrix or vector so much, but as a set, X1, X2 up to Xn, right? So this will be a subset of our, so just the real values. So it'll be, in general, be RD, but for now, D is going to be equal to 1. Okay, so these are just going to be scalar values, a set of these scalar values. It's an X2. And then there's also going to be Y, which is also going to be a set, Y1, Y2, up to Yn. And these are going to be, so scalar values. Oh, this should be a subset. So it'll be a subset, meaning elements from the set of real values. And so both of these, and often We'll actually think of this as actually a set of these pairs, right? So we can think of x1, so y1 as a pair together. The fact that there are n of each of these, the indices that are the same are going to so correspond with each other. So it's going to be important to align x2 with so y2, and so think of them as the set of these pairs up to xn, so yn. All right, because the x and the y values are going to be so correspond with each other. All right, so and so we're going to call these the x values are going to be the explanatory, so variables, or so values, and the y values the dependent variables. And the goal of linear regression, so the goal, and I'll draw a picture of this so it will make sense beyond just the equations I'm writing up here soon. But the goal of this is to learn a function f of f of x, which approximately is going to give me the value of y. Okay, so I'd like to learn a function from the explanatory variables that are explaining what's going on, and they're going to give me a value, y here. Maybe I'll make a, so this is like an arrow, right? So a function, right? So if I think of a function, we're going to think of as the x values down here. And so later we'll make this so it's multidimensional, right? And these are the y values. Those are in the real numbers, right? And so, if I have a function, right? So if a function has the property, so has a property that for each value of x, right? So for any value of x, there's going to be exactly one value of y. Okay, it's not necessarily true the other way around, right? If I have a value of y, there might be multiple values of x, which are so generating that value of y, but it's a function from x to y, and I'm trying to learn from x to y, right? So I want x to explain what's going on, and y to somehow depend on this, right? So I wanted to learn a function like this. In particular, what we're going to talk about today are linear functions. Linear function. Okay, so a linear function means that it's going to be a line here. Okay, so that the function is going to be a line from x to y, and so that's going to have this like relationship where f of x is going to need to be, if x is just in one dimension, what a linear function means is that I have ax plus b, right? And this is going to give me the value y. Okay, so I want to learn this function on x, right? And so I've got the only ways I can kind of control and describe this red line is by determining these parameters a and b here. Okay, so I want to learn this linear function, right? And it somehow should depend on this data, right? So I want to learn, this function from the data. So if I have a linear function, this case is actually invertible. Aside from if a is 0, or if that means I can map back from y to x. But in general, this is, well, we're going to consider functions when we look at, so like the polynomial version of this, it's going to look more like the green function. It's not necessarily going to be invertible. So in general, we want to learn these functions. That's kind of describing a relationship from X to Y. Okay, so there could be a discussion of are the values of X. So there's what's called a causal relationship here. We aren't really going to get into this. This is kind of an advanced topic within data analysis, and it's actually quite tricky and subtle. There's I would say it's the area where there's like active debate. Should you trying to only learn relationships which are causal or not? In some sense, that sounds like, yeah, you should only learn relationships and functions from X to Y if there is a causal relationship, however hidden it might be, from X to Y. And so that seems like a good idea. The problem is to prove there's a causal relationship is very tricky, and the techniques are sometimes much more complicated. And so and not necessarily as like effective in practice. So, so we aren't going to get into that in this course, but just kind of something to keep in mind. It's kind of like we're learning some X causes Y, but I'm not explicitly, saying this here. But if that's your first kind of way of thinking about this, so that's probably okay. So let's look at some actual data here. Okay, so this is an example from the book here, and again, what is going on here is I'm giving some values of, this could be from some people, this could be their values of their height and their weight, right? And so the way to interpret this is that this is the set X, this is the set Y. This pair here, this would be X2, this would be Y2, right? So there's a value X2, it's a height of 66 inches, a weight of, like 170 pounds, right? So the weight of 170 pounds, so would be like Y2, right? And so then I can plot this, and this corresponds with a point in the graph, right? This, of course, 68 and 170 looks like it's this one. So, so right here, right? So this data point corresponds with this row in this chart, which is this pair kind of X2, so Y2, right? Okay, and I can plot, so all of these points, right? And then what I'd like to do is fit a line, so through the points here, right? So there's a line which is A, B, which is, I can think of this as a function from X to Y. And so this function will be AX plus B, right? For some choice of A and B here, right? For every value A, for every value X, right? I'd like to, so what I'd like to do is to make a prediction using this model of what is the value of Y, right? So if I use this model here at 68, I'm going to actually get a value here, which is slightly different. Maybe this is going to be 172 instead of 170, right? So the value I had for this data point was 170, and maybe this model, this red line, is predicting that it's going to be 172 instead. Okay, so I'd like to find a line, and then I can use that function to try and predict the value Y, right? So in this case, if I looked at this data point and say, okay, this model is wrong, perhaps, right? It's not giving me 170, I'm getting 172 instead. But that's not quite the point that's so that's happening here. The idea is that, we're gathering data, and the data might not be so perfect. There's probably some noise in the data. In fact, we're going to often think about the model, the underlying property here is that the data is coming, from this line, but that there is then some error associated with the y value. And maybe there's like a normal distribution on the error here. And so when we get the actual reading, right, so that the actual y value we observe is something like f of x plus some noise. Okay, and in particular, there's an underlying assumption, which I won't totally get into, but that there is a true function, a linear function, plus some normal noise, and the normal noise has a mean of 0. That means it's going to be unbiased. It's not more likely to be up or down from the actual value. The mean is 0, and there's some standard deviation or some variance in there, and I won't really need to specify exactly what the variance is. If you remember, when we started with this Bayesian inference, part of the course, we said assume there's some normal noise on this one-dimensional data, and we found the maximum likelihood estimator, and then we solve for what the maximum likelihood estimator was. That did not depend on the variance in that noise at all, and the same is going to be the case here. So there's actually some line, but we assume the observations come with some noise. This could either be that there's some sensing noise. It could also be that there's some underlying pattern that's going on, and there's personal variation in the data. There are external factors we can't understand or measure, and so we're just going to accept that as noise to go after a model which is simpler to understand. All right, so that can mean a few things here. And so the real power of this, though, okay, what I'd like you to look at now is this last line here, right? And this is when I have a height value, 69 inches, and I would like to try and predict what the weight value is going to be here, right? So I have a question mark down here, and so I have the height value, and I don't have a recorded kind of weight, right? So I'd like to make some sort of guess in this place where I don't have any data, right? I don't have data yet, but if I have a model I've learned from where I do have data, then I can use this to kind of try and generalize the data I have to say, let's find a pattern in this data so that when I have a new data, I have a new x value, the explanatory variables, which should do the explaining, I can try and predict so what the weight is going to be, right? So in this example, if I know someone's height, is it that helpful to know, so about what their weight will be? But you can imagine other examples where, so say if I look at students who are coming into this class, and there are some prerequisites for it, and I can look at your grades in those prerequisites, and I can say, how well do I expect you to do in so this class, based on the grades in those prerequisites, right? And so like if the grades were low, I'd say maybe you should take this other course first, or to help you so kind of get up to speed or get a little bit more practice in certain things. So because I've modeled based on past students that your expected grade in the class is not very high, right? So whereas if you do this other thing first and you get your grade higher, then your expected grade here will be higher, right? So you could also say, how much do I expect you actually learn from this class? Based on your grades. Grades aren't the only thing I really care about if you're learning stuff, but so how much do grades correspond with how much knowledge you actually kind of, so took home at the end of the day, right? And so that's something maybe so harder to measure, right? So I'll give you, like we said, there's a final exam at the end of the class. The final exam is not the, so like the perfect measurement of how much information you gained at the end of the day. But, I could say, well, I'm going to select a handful of students and say, look, I'm going to give you like a really extended exam. And this maybe it has some like oral components to it, and I'll test you sitting with me to do some like stuff in Python, and I'll get a more comprehensive score. And I want to say, okay, how well did those scores that students got in the longer exam correspond with grades on the true final exam, or so in the course, right? So I want to see how well does a more expensive measurement generalize to this other data I have. These are the sort of things you can do with like a regression model. So we'll talk about some other examples of using this kind of so like a little bit later in the course. But I want today I want to focus on like what is the right way to decide what is the right line to find. Like, so how would I say one of these red lines, these functions I'm modeling, are better than another line, right? I've drawn this line up here, right? So I didn't tell you how I found this line. And so before I tell you how to find it, the thing you would typically want to do is write down some sort of objective function of what is a good line, right? And once I decide what is a good line, the modeling step, then I can say, okay, now how do I find the best line under, so that way of specifying, right? So let's talk a little bit about this. All right, so let's say I've got, so some data, so I've got a data point here, and then I'm going to choose a line which is going through these data points. It's kind of close to them. So I want to say, how good is this line with respect to this, so data, right? And so let's say, right, so this data point here is, say, xi, so yi, right? Remember, this is the xi coordinate. This is the yi coordinate here, okay? And now I'd like to, so measure the error. And the error is kind of should be some notion of how close this data point is to the line, right? This makes sense? So you think I want to measure how close it is to the line, but I want to do this in a fairly particular way. I don't just want to measure the closest distance to the line. This has a number of kind of actually challenges to it that we will talk about in like the dimensionality reduction part of the class that are different. Instead, I want to measure the distance in the y coordinate. So there's another point up here, which is what I call yi hat, okay? This is the predicted value. This is going to be, if I take the line of xi, I'm going to get out a value yi hat. So this is my predicted value, okay? And this kind of corresponds, right, so with yi hat here. And so I want to measure the difference only in this y coordinate. Okay, so this difference between these two values here, this difference, so this is called, so Ri, this is going to be yi minus yi hat, and so Ri, yi minus yi hat, this is called the So residual. All right, so this is the difference in between the observed value minus the predicted value. Or if I have a function, generally yi minus f of xi, right? So this is the error on this, so one data point. You could think of instead doing something like this distance here, right? The closest distance to the line. This is actually, if I draw this, this peach line here, this is actually closer. That point on the line is actually closer, but this is more challenging to work with because it's a little bit harder to compute. It's not so too hard to compute. You can do it like a dot product, and we'll see later in this semester how to do that. But it's also measuring something that is not just the error in the prediction, but it's also somehow accounting for some error in like the xi value. And this might be relevant, but we're going to assume the xi values do not have any error in them at this point. Okay, so that's basically baked into this assumption that the xi values are accurate, but the yi values might not be accurate. Okay, it's the other thing this does is it allows us to convert between so units here. Okay, so this xi direction, this is x, and remember that we had in the previous example, this was the height, so in inches, and the yi value was this was the weight in pounds, right? And so if I'm measuring that pink value, the peach value, it's somehow some combination of inches and pounds, and this is kind of weird. Okay, so it doesn't actually have a units which are so well defined. Whereas if I look at the difference in the yi values, that's just a measure in the y coordinate, which is just pounds. So doing this is totally fine. Okay, so I don't have to worry about the change in units. In fact, regression, linear regression in particular, gives you a nice way to, so to convert between units here. Yeah.
So the regression of x based on y be the same as the inverse of the regression of y based on x?
No, these would not necessarily be the same. And we'll get to I'm still building up to the formulation, but we're measuring the residual error in the y, whereas if I were to measure the residual error in the x, it's going to be kind of going in this other direction here, in this direction instead.
But
and
also, if there's like no, we can't have causality with causes y, is there any reasonable reason that we use x with one to the x?
Yeah, so the reason is typically going to be that you think you can get better access to the data in X than you can in the data in Y, right? For instance, it could be like you have some, potential customers of your company, right? And certain customers or certain customer behaviors lead to more or less profit, Y. But I don't necessarily know that for potential new customers. Should I try and recruit this person as a customer? Or if I'm like a plumber, right? And so I have a bunch of past jobs with customers, and I have the expenses of what the job will cost me, and I'd like to bid a job slightly more than my expenses, so I'm making a profit. But I don't necessarily know what the expense will be until I actually do the job. I have past jobs experience, and I see a new potential job. I have all the details about it. I want to make a prediction of what my expenses are going to be, right? There's probably a causal relationship there, but it could be the expenses are somehow dependent on the bid and some other stuff that comes in that's more complicated. Right, so I'd like to make a prediction, but I don't need to necessarily establish a causal relationship here. This is more of like, this is a really interesting area, and it's an active area, but it's kind of we aren't going to totally get into this. Use it as kind of a guide. We typically want a causal relationship from X to Y, but we're not going to formalize that or trying to argue that that's the case. Think of we have access to the data in X, and we think the data in Y depends on the data in X in some way. Not necessarily a causal direction, but it somehow depends on it. So, okay, great. So we have this residual, and for one data point, this is going to quantify our error, right? We're going to measure the error as, so this residual. Another advantage of this residual is we'll see when I have a polynomial function. Remember, we might have these curvy functions as well, where we make a more complicated function. I can still measure the residual just in the y coordinate here. I don't have to worry about, okay, the closest point onto this curve. That turns out, find the closest point onto a polynomial curve is a more so complicated question. Yeah, in fact, I just had like a recent research paper on this. It's actually, it took us, there's a bunch of pretty tricky things about that. Whereas if I just measure in the y direction, this is what everyone does. It's very straightforward. So, okay. And in the next lecture, we'll actually see how to do it and see that it's just a simple extension of everything we're doing. Okay, so this is one data point. Remember, I've got n of these data points. I'd like the evaluation of how well my line is doing. I'd like all these residuals to be small. So I want to aggregate all of these together, and the typical kind of I'll say the cost of a, let me just say so function, so f, or L if it's going to be a linear function on x, y. Okay, well, we're going to write this as the sum of squared so errors. Okay, so this will be the common formulation. And let me write this down, and then we can kind of discuss how to think about this. So I'll write the sum of squared errors, SSE, right? And this will take in the data, our input, x and y, and we'll take in a, so a function. In this case, we're just going to be talking about a line. Okay, and this is going to measure the sum over, it's the sum of squared errors, right? So the sum of the difference between the yi's and the prediction, the xi's, and we're going to square these before we add these up. Okay, I can also write this, as there are different ways which are equivalent. I'll write them all here. Yi minus some prediction, yi hat, right? Remember, yi hat was equal to L of xi. This is squared, or just the residuals squared. All right, so something about the residuals. Notice I said this was the difference between y and y hat, right? But it's like a sign difference, right? If I go back to this picture, I could have had a data point. For instance, if I look at this data point here, it's larger than the y value there is larger than y, the corresponding y hat value, right? So then I would subtract them. Yi minus y hat in this case is going to be a negative value, whereas in the light blue case I've highlighted it's going to be a positive value, right? So these residuals can be negative or positive. In some cases, someone might write the residual as y hat I, so minus yi instead, swap the order of these. It ultimately does not matter very much, because when we consider these in our error formulation, we're squaring them. And when we square them, the sign goes away, right? The square of a negative is the same as the square of the same value if it's been so positive. So if I swap yi and yi hat, it's going to give me the same value inside the squared.
Is this like the variance?
So residual.
Standard deviation?
Yes, like the variance here, right? So we should think of this as so like the variance, maybe, yeah. So you could think of maybe, I think yi hat is like the expected value, right? And this is the yi would be like the observed value of my, say, random variable. And so then I'm taking the average or the sum in this case, but you could think of doing an average instead of the squared difference from the expected value. That would be a variance. Yeah, great. So it's a lot like the variance here, right? Good. So the fact it shows up like the variance is exactly a good way to think about this. We'd like to minimize the variance in our estimate here. And so when often when a statistician looks at a regression problem, that's how they kind of are trying to formulate this. If I put a 1 over n multiplicative factor in front here, this is going to look a lot like the variance sort of definition. If I put random variables, an underlying process in here instead of just the observations. Right, great. So that's a good connection to make. Yeah, so why are we using this sum of the squared errors, right? So there are a number of, rationales here. One is this I'll just write this down. It looks, so like the variance. Okay, and the variance is a quantity that's well understood and studied in statistics. It's a nice way of quantifying the deviation from some sort of expected value. There's a lot of nice, sort of mathematical properties. So if you were to, try and extend this, and you were to write down the maximum likelihood estimator, right, of something over the space of these, over the space of all lines, you can actually derive the sum of the squared errors exactly, right? You can derive this formulation of the sum of the squared errors. I'm not going to do that in this class. It's a bit more complicated than the case we did with the mean, where we're just doing the variance estimator, but it basically looks the same way. You assume there's normal noise, you write down you assume the observations are IID, you write down the joint likelihood function, you do a negative log likelihood transform, and you get something that looks like this. It's a bit more complicated, the steps, but there's another way of justifying this from normal deviation from the expected value. All right. So another reason to think about this is that the sum of squared errors of x, y with a function L, right? This is equal to the sum I equals 1 to n of the residual squared. And I can actually write this as if I write all the residuals into a vector, then it's just the squared norm of, this residual vector. I've got a bunch of, if I'm measuring the distance, I want to think of just kind of some dual or transpose of this, where I have some R kind of vector here, which is R1, R2 of Rn, right? And I want to say, how long is this residual vector? Well, I measure this. There are other ways to measure length, and there are other ways that people consider in this case, but the standard way that we talk about in this class and in most cases is just the norm of that vector. That's the Euclidean length of it. And I'm just going to take the square of that. If I minimize the square root of it, it's going to give me the same answer. Okay, so I'm just measuring the length of this residual vector. If I want to optimize that, that's the same thing as like the sum of the squared errors. Okay, and then the last reason is that there's going to be a simple, closed form, so solution. I'm going to be able to write down a very simple algorithm that's going to solve for the optimal L here. Just like I did with the case of the mean of one-dimensional points, I'm going to write down an algorithm which is super simple, and it's going to generalize to higher dimensions and with polynomial curves and a lot of other settings, that I can solve this form simply. If I were to plug in a different cost function, it wouldn't necessarily work. I'd have to resort to, to other approaches. Yeah.
So is there an argument against using something like the sum of, like, just the absolute value of the
Right. Yeah. So there is a formulation where you write down the sum of the absolute values of these. Yeah. So it's not going to look like the variance. It's going to be the maximum likelihood estimator. If I think about Laplace error instead of normal error. So I can derive a version of that as well. And it's going to be the L1 norm instead of the L2 norm squared, or no, just the L1 norm here. But it's not going to have a simple closed form solution. Okay, so it's going to be a lot harder to solve. I'll be able to solve it with like some linear programming, and that's so you can write it down and do linear programming, but that's more complicated. This one will also talk about a gradient descent solution, which we'll see after fall break. And the gradient descent solution works better in this form than with the form with the sum of the errors. And we'll see why when we talk about gradient descent. You can kind of solve it there, but it's going to have some more challenges with that. Yeah.
Sorry, just to confirm, the second point is saying that finding the maximum likelihood estimate, which minus the most likely, is found by minimizing the estimate. Yes.
Right. So I want to minimize. In fact, you want to maximize the negative of e to the power SSE or something like that is equivalent. But I mean, these are monotone transformations. So it's the minimum of this will be the same as the maximum of the maximum likelihood written down in a way I'm not going to do in this class. Yeah.
So the MLA points, even this is the best estimator when you assume that the noise is normal.
Yeah, when you assume the noise is normal. If I go back here, and for every, where did I draw this, right? So on that data point, see that red little bump up here, this area, I assume that this observation came from this line with normal noise in the y direction. That's what the underlying model is saying. And if you write down the MLE formulation of it and you do some algebra, you can derive the sum of squared errors.
Sorry, so what do you mean by the formula?
So normal noise is, so equals, there's some constant in front here, and it's e to the power, kind of yi minus yi hat, right? Which is kind of the expected value squared divided by sigma squared, right? So this is the normal distribution. I don't need norm here. I can just say the difference between these values squared. Right? So if this is the normal noise that we had talked about earlier in the semester. Yeah. And this is the most common form of error for a variety of reasons. Other ones do show up and sometimes they're better, but by default, we'll think about this, the normal noise, and that will directly correspond with the sum of squared errors. Okay, I want to say one more thing about errors, and then I will give you a short break. It's often useful to talk about the root mean squared error. This is often called the RMSE, and this is very similar to the RMSE of x, y, and some line is going to be, I'm going to start with the sum of the squared errors. That's going to be then yi minus the line of xi squared. But I'm going to take the mean instead of the sum. So by the mean, I put a 1 over n in front, right? So this part turns it into a mean, which is like the average. And then I'm going to put a square root over it, right? And so this kind of square root here, right? So this is going to root, and so this kind of fixes the units. The advantage of this, the sum of squared errors is in the squared units that we talked about for the y value, like the weight. It's the sum of the squared weights, so the errors in terms of square weights. This is like from variance to standard deviation. I want it back in the original units. And I typically take the mean. So it's saying, what is kind of it's kind of like the average squared deviation. It's not quite that. It's the, because that would be taking it's the square root of the average squared deviation, and it should be back in about, it's kind of like the standard deviation, and it's like saying what is the expected, something like the expected size of the residual. Not exactly that, because of where the average and the square root fall in each other, but this is easier to talk about as a unit. When you're to write down a value which you want to look at, is this a good error, is this a large error? The root mean squared error is more so interpretable, okay, than the sum of the squared errors. Because as n grows, the sum of the squared errors grows. As the units change, it's not in the same units as the original data. This is in the same units, it does not grow with n. So great, so let's take a small break for like, so 4 or 5 minutes, and then we'll talk about how to compute this in a simple case, and we'll go through an example in Python. The maximum likelihood estimate. Yes, we talked about this in lecture, in like the 4th lecture, maybe when we talked about Bayes' rule, we talked, and then we got rid of, we assumed that the prior was uniform. Right, but then we write down the likelihood, which was given a model, what's the most likely? I can evaluate the likelihood of a data point given that model. Right? And then I can take the joint likelihood over all the data points, right? To combine them together, and that's the joint likelihood. And if I want to maximize that over all choices of models, then that's what we're going to do next. How do we find the line that minimizes the sum of squared errors? It's the same as maximizing some underlying likelihood, assuming some normal nodes.
Basically, you can't.
Is that supposed to multiplication sign or
That's a minus sign. Yep.
Oh, okay. Yes. Yeah. Hopefully we'll get it all together.
So let's get going again, so we can finish up the lecture. So okay, so what we did up till now is we said, okay, we have as input this x, y, and we so interpreted that this was in this case x is just so one-dimensional. So and in fact it's so a subset. So this is a set from R cross R. Okay, and then we said so the goal is going to be a line L that's going to be a function ax plus b. So L of a b of x is going to be approximately equal to y, right? And what we want to do is to minimize the sum of the squared errors, right? And so this was x, y for for L, and really here L. The way to think about this is there's some L, and this L is parameterized by A and B. Okay, right, so what we really want to write here is that this will be the sum from I to n from yi minus axi plus b squared. Okay, and we want to now how do we find the best values of a and b here? Okay, which is going to minimize this function. Okay, and so this is kind of like how all of machine learning is going to work. We're going to write down some model in an explicit way like this. Okay, so our model here, right, is this line. The model needs to look like this, and it's going to have these parameters a and b, and then we're going to have this will be the model. And we're going to have with it a cost function. Okay, and there's going to be some parameters. So parameters, and we want to optimize these parameters under this sort of framework we have. So linear regression, aside from just the mean of a data point, is kind of the simplest model. So we're doing this one first, and we'll see a lot of the cool stuff with respect to just linear regression. We'll do cross-validation. We'll generalize this. We'll do gradient descent, all with linear regression. This is the basic form here. And so in particular, what we want to do is we want to find the arg min of A and B, right? And this will be an R squared. These are both some real values. We'll call these A star, so B star. These are going to be the optimal values, which are going to, so minimize the sum of the squared errors. Okay. So for most of this class, we're going to focus on the sum of the squared errors kind of objective. We did it with the mean. We're doing it now. The generalizations of linear regression are going to also use this. The clustering formulation we're going to look at is going to use this. The dimensionality reduction formulation we're going to look at is going to use this. There are other formulations, right? The sum of the absolute values of so the residuals is an example of another one. There are plenty of other ones as well. This is mostly what we're going to look at because these are the most common things to solve because they have simple solutions and they can be derived as before. In classification, we'll start with this and then we'll say, well, we're going to change it a little bit. But so that's a little bit more complicated. By that point, hopefully the generalization beyond it will be a little bit, it'll be easier to comprehend. All right, so we wanted to find the minimum values of A star and of A and B, which are called A star and B star. That'll give us the best line, the one that minimizes the sum of the squared errors, right? So how do we find these values A and B? All right, I'm going to give you a procedure how to do it, and then I'll talk about some intuition behind that procedure. And then we're going to, next lecture on Thursday, we're going to talk about how to do this in higher dimensions. And we're going to do it entirely with linear algebra. We'll do some like very simple linear algebra. We'll deal with vectors or averages or something here. But the linear algebra formulation is actually a little bit cleaner, but I don't want to present it first. And that one we'll talk about the meaning, a little bit more of like why that's the so why that's the right solution. Okay, but this solution is a bit simpler. Okay, so now I want to solve for A star and B star. Okay, and I'm going to give you a fairly simple kind of a few steps how to do this. One, I'm going to create, find some averages. This is going to be the average of all of the X values. Okay, Xi. So this is, again, we're just solving this in the simple case of a line in X is one-dimensional. And I'm also going to find the average of Y. Okay, and so these points will be kind of interesting because as we'll see, we're going to have you know, some data. We're going to find a line, and this is going to be the average. Think of if I have a bunch of these data points, it's going to be the element-wise average. This will be X bar, Y bar, and it turns out the optimal line will go through this point. So we're going to use this point, and we're going to start by basically centering our data so that the average of the points is actually going to be at the origin. We're going to shift all the data points onto the origin. Okay, so that's the second step here. I'm going to call this X, so tilde here. And this is going to be the set. The first element is X1 minus X bar. The second one is X2 minus X bar. Xn minus X bar. Okay, so what I've done is I've subtracted the mean, the X bar value off of all of the data points. What that's doing is it's the new data points under X tilde is going to be centered on the average. The average will be, now the X value will be 0, right? If I recalculate the average after subtracting X bar from everything, you can kind of check and verify this, but the average will then be 0 afterwards. And we'll do the same thing with with y here, y1 minus y bar up to yn minus y bar. Okay, so I've centered all the data, and this is kind of like, now I'm, you know, if I'm minimizing the variance, well, now I'm just minimizing the mean of it. The expected values are now kind of closer around 0. So it's going to be a little bit easier to work with. Once I've done this, it turns out I can directly solve for the slope. Remember, our model here is L of a b of x is equal to ax plus b. And so this a value here is like the slope of the line. And so the slope of the line will be how much does x vary after I've removed, you know, I've centered it. How much does x vary correspond with how much does y vary? And it, you know, it turns out you can write this, solve for the slope value as the dot product between y tilde and x tilde, right? I treat these now as vectors, right? And this is divided by the norm of x tilde here, the norm squared, okay? Okay, so it's a dot product divided by a squared norm, okay? I'm not totally gonna explain this. You can rewrite this if I expand this dot product. If you remember, this is y tilde norm times x tilde times cosine of some angle between them. If I think of them as n-dimensional vectors, divided by the norm of x tilde squared. So these guys cancel and the square cancels. And so now I'm kind of getting something like looks like a slope. This is the amount of variation of the y coordinates divided by the variation in the x coordinates. Okay, so I'm kind of seeing I'm changing the units here, right? A is doing work to change the units. B is in the same units as y, right? A is converting from the units of x to the units of y, right? And that's what's happening here. I've got, it's the units of y divided by the units of x. So that part makes sense. And it's kind of the variation of y divided by the variation of x. And there's this cosine theta, which is dealing with, should it be negative, should this be positive, and some other, how correlated are these? Yeah, I'm just going to kind of wave my hands at this point. So we'll talk a little bit more about this on why the generalization of this makes sense on Thursday. Okay, and this turns out to be the optimal A star. Again, I promise you there was a simple solution for the optimal value. Then I want to solve for, so B star, right? B star, B is the offset. B is telling me how much do I shift the line up and down. A controls the slope. And remember, I wanted it to go through this, so I wanted it to go through this mean here. So the offset is B. If x is 0, then how far below or above the origin is it? And this is something I can do to slide the line up and down until it hits this mean of all of the data. Okay, and so you can solve for B as just y bar minus A star times x bar. Okay, so if I already know the slope A star, okay, then I can say, well, this equation should hold for the mean, right? It should be that y bar is equal to A star x bar plus B, right? So this is the equation I want to hold. And so I solve for B star in this equation, right? So I solve for B star, and this is my solution for B star. This forces the line to go through that mean point, okay? So the offset does not have any bias into it. All right, so this is, like I said, there was a because the sum of the squared errors, there's a simple solution here. The solution using linear algebra, which we'll again do on Thursday, is actually going to be even, you won't have to do separately for A star and B star. You're going to combine those together into one vector. That vector can be even longer, and then the solution is kind of, will look even simpler than this somehow. And we'll talk a little bit about a bit more about why that's true. You know, you can verify this by, again, you have a cost function that has, it's a sum of squared errors. So you can take the first derivative of it, or the second derivative of it, and set it, so the first derivative of it, and set that equal to 0 to verify it's the minimum of a cost function. We'll talk more about the shape of these cost functions when we're talking about gradient descent after fall break. But so kind of as a procedure, again, very simple, very straightforward. You should be able to calculate this in Python to solve for this. Great. And unless there are any technical questions on what's in here now, I'm going to go show you how to do this in Python. This simple step, and also how to plot things like that plot that I showed earlier. Okay, so there's again, this is linked off of here, and we'll be doing a number of kind of collab examples in this part of class, but it's this link here. Here we go. Okay, so this is just linked off the webpage. Again, when you're doing homework, you're welcome, and the point is for you to start with the collab files. Things are going to get a little bit more complicated, but if you start with the files I provide you, it should make it much more manageable, even if you've never seen Python before. Okay, and again, we're going to use NumPy, in this case, so far, only because we're going to store our X and our Y values as these arrays. We're going to store them as vectors, as n-dimensional, 2 n-dimensional vectors. That will keep, say, the first the data points aligned with each other. Remember, I thought of them as a set, but they were really a set of pairs, and it's easier to keep them separately, the X and the Y vectors. Okay, and we want to take the averages of, we'll need these averages of X and Y. We'll use these later. Okay. And I'm going to do some plotting here, right? So I'm going to do Matplotlib. We saw this in the very first Python example. Not sensing my finger properly. Let me try something else. Okay. 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 So it's right. So we're doing this, and this Matplotlib. We need this. Okay. Yeah. If you want to. Yeah. Okay. And we're going to plot this as a scatter plot, right? So plotting in Python is very very simple. It's got a lot of nice built-in functions. You can just call PLT scatter, takes in X and Y. The S tells me how large are these data points. If you notice the red one I plot here, the average is a little bit bigger. If I want to make this even larger, then I change this to 200, and okay, it's a little slow today, but then I can put the color as blue. Okay, so now I see that this is the average of X and Y, and that's that number tells me how big it is, and blue and red are just as the color. And then PLT show tells it to plot. Okay, so you can now plot these scatter plots. Very simple, right? I can grab this from here, and now I have access to it. Okay. Now I want to actually solve for this line, right? This line I want to plot. And remember, I'm going to do the X tilde and Y tilde. I'll call them XC and YC in this here. And so I do Y minus this. What is going on here? This is kind of neat, right? X and Y are vectors, and average X and average Y, those are scalars. That's a single value. When I subtract it, well, it's subtracting the scalar from everything. Python knew that's what I wanted to do somehow, right? So if I want to subtract a scalar from everything, I just do this, and it knows kind of, if you're used to like typed systems, this should be kind of like maybe a little bit uncomfortable, but it's definitely very convenient, and the developers of this put a lot of thought into it. And then if I want to take the kind of this calculate A star, remember it was just the dot of XC and YC divided by the norm of XC squared, which is just XC dot XC. Okay, and that's A star. That's A star, and B star is the average of Y minus A, which I've solved for, times the average of X. Okay, and again, I've multiplied by a scalar by a vector, and that's an element-wise multiplication here. Okay, and I can print this mean point and print A and B. This is my solution. My line is now two values, 8.2 and negative 383. Yeah.
You're supposed to divide the A by the squared norm.
Divide A by the squared norm of X. Yeah, that's actually happening right here. I've done division by the squared norm of X. The XC dot XC is equal to the squared norm of X. Yeah, so I can take a dot product. If I take the norm and then I take the square of it, the norm calculates the square root, and then I re-square it again. This is a little bit better way, but it's the same kind of, it's the same calculation, yeah. Okay, so this is an interesting thing, right? This line, I'm gonna plot the line next, right? The line is two numbers, right? That two numbers describes my model, right? This kind of, we'll see this over and over again in more complicated ways, but I've reduced my model to just two values instead of having to think about what is the geometric shape of it. Okay, you can also do this a number of ways within Python automatically. This is some built-in function in NumPy, polyfit, which finds a degree 1 solution. On Thursday, we'll look at higher degree polynomial solutions, and you just increase this value 1, for instance. But it gives me the same solution. Just takes it x, y, and some parameter, right? So you know, in practice, you don't have to implement this. Python does it for you, but just to see how it works. And so then, remember, the goal of this was to predict a new value, right? So I had this missing value 69 for the height of my data set. I want to predict the weight. I took A and B and I predicted the weight, and it's 183.03 or something like that, right? So that's my prediction. I can use this function that I have learned to make a prediction now. And this is kind of the power of what's going on here. I can make a prediction. Okay, and then finally, let's plot this all together again. Okay, and I'll just show you, and then I'll step through. There's a couple things that might be useful to understand here. Well, I'll talk through it while it's loading. Okay, so yeah, okay, so now I've plotted my red line, which is the model, and it goes exactly through the mean point as I promised. It's close to all the blue points, and in fact, it's minimizing the sum of the squared errors. I've plotted the black point at wherever so the value 69 down here. I plotted the prediction here. This is 183, and that's the prediction of the point that was missing before. I wanted to the plotting is a little bit mysterious. If you haven't seen before, you probably did it for your homework 1, where you just followed the example I did in Python, right, in class before. But you get this line space, and this gives you kind of a NumPy array of the sort, and it says, I want values between 60 and 76, which is the range of my heights, right? And I want to have 50 different values in between, evenly spaced them. And then what the line does is it takes this as a vector, multiplies it by the scalar, and it adds the scalar to it, and it gives me the line as the output. This is actually y values here. So when I plot this h and the line, it knows, the plot command knows it's supposed to be kind of a curve. And I said, I want a red curve with that's connected as a line. That's what the red dash means. And so what might be useful to see here is if you print H, right? H is this line space. Remember, these are values between 60 and 76, and there are 50 evenly spaced points. What people commonly might do is say, well, I'm going to do 51 that way, because it always includes the first and the last one. That way it might divide more evenly, although I don't get these weird fractions in between here, but it's really, that's what the line space is. And if I were to print the line values this same way, let's see, print line, it's again going to give me all the y values that correspond. And so the plot is just plotting these individual values and connecting these together. This will be great because when we plot other functions, instead of just linear functions, they work the same way. It'll know to connect them together, and I can have whatever resolution I want. And you choose a resolution until it looks smooth. If it looks too jumpy because the resolution is too small, then increase this number 50. Here, I know we'll have a higher resolution. For a line, I really only need 2 points. But if I have a more curvy function, I'll need more points to capture it. All right, so that's pretty simple, right? So how to plot, how to calculate it, and we'll see how to go to higher dimensions and polynomial functions on Thursday.
Oh, yeah.